When most of us first think about probability, we often associate the word probability with chances or likelihood, and there are many other terms, but probability is really something more interesting than just saying chances or likelihood. But let's just go ahead and start with the mathematical definition. So we have some sort of set S, which we'll denote to be the sample space of possibilities. And within that sample space, we have some sort of event that we're interested in. So off to the side over here, let's say that our sample space consists of an event which is a die roll. So we roll a die. And so the sample space is the set of all possibilities. Well, that's going to be the elements 1 through 6. So you roll a fair six-sided die. All right, here's your six-sided die, and this has, all these different number of dots on it. And so what we want to figure out is basically what's the likelihood of a certain event happening. So I'm going to define an event now. And so an event is some subset of the sample space, and what E actually represents is basically some outcome within the sample space that we want. So some set of outcome or outcomes from the sample space. So for instance, we might be interested in the event that we get maybe a number, we roll a number that is divisible by 3. So we want a number divisible by 3. And all we mean by divisible by 3 is that if we, for example, take 3, we divide it by 3, we get an integer. We take 6, we divide it by 3, we get an integer. But any of these other elements, 2 is not divisible by 3, since 2 divided by 3 is 2/3, which is 0.666 repeating. And so that's not going to be divisible by 3. So the elements within the sample space that we're interested in are the elements 3 and 6. And so the probability of an event is defined, by the number of ways in which that event could occur divided by the size of the sample space. So this, in other words, the size of set E divided by the size of set S. And what we're assuming here is we're assuming that S has outcomes that are equally likely. So when we roll a die, we assume that a 6 will pop up an equal percentage of the time as a 5 or a 4. Basically, 1/6 of the time you'll get a 1, 1/6 of the time you'll get a 2, 1/6 of the time you'll get a 3, and so on. So if we were to roll that die 12 times, roughly speaking, we could expect 2 of everything. And that's what we're going to kind of explain a little bit more with regards to probability, because it doesn't have to happen, right? All of these things are up in the air. This is chance. So it's not unheard of that you could roll 4 3s in a row. Now, of course, the likelihood of that happening is small, but that's still larger than, for example, rolling a die 6 times and getting all 5s. Okay, so to define this probability of this event up here, the probability of event E is the size of that set E divided by the size of the sample space. Now, the number of elements that we have in there is the size of that set. So 2 elements that we're interested in rolling, or 2 sides that we're interested in showing when we roll that die, divided by the number of possible outcomes, which is 1/3 or approximately 33%. Now we got to be careful how we interpret that, because we can't just say 33, if we roll a die once, 33% means nothing, right? Because either you do get a 3 or a 6 or you don't. And so we need to think about what this 33% really means. And this 33% basically means that if I were to roll that die multiple times, many, many times, after many rolls, and whatever that means, right? Many in mathematics really kind of refer to this idea of infinitely many. after many rolls, we would expect 33% of the outcomes to be a 3 or a 6. Now that's not going to be exact. You could roll the die. If you roll the die 3 times, for example, you may not get a 3. If you roll the die 3 times, you could get a 1, a 2, and a 4. That may not be enough times to really see that 33%. But if you continuously roll this die over and over again, and if this is the roll number, and this is the percent that E has happened, so 1/3 is down here somewhere, right? So the percent of the time that E has happened. Well, we may roll the die once, and the outcome could very well be something other than a 3 or a 6. It could be a 1, a 2, or a 4, or a 5. And so then we roll the die again, and we maybe get a 5, right? So there's still 0% of our rolls have resulted in getting that event. And then the next time we may roll it and we get a 4, so that still doesn't count. So what we'll end up seeing is if we keep track of the cumulative percentage, the percentage of the time that one of the elements in event E popped up, what we'll start to see is maybe some slow increase in this and maybe slow increase. And then so what we'll see over time is that the percentage of 3s and 6s that we get may jump up, may jump down, but eventually what we expect to happen is that in the long run, for many, many rolls, we would expect 33% of those outcomes to result in either a 3 or a 6. So what we really are referring to is after many, many repetitions of this experiment of a die roll, only then should we actually see that 33% of the outcomes start to result in the desired outcome, which is either a 3 or a 6. Okay, so that's the basic definition of probability. Now, probability is incredibly useful. Here's one fun, maybe not fun, interesting example of Kristen Gilbert, who was at one point the nurse at a VA, Veteran Affairs hospital in Massachusetts. And what started to happen was that this person, when she was on duty, they started to notice that some of the patients were actually going through, would die, right? And so this was due to, I can't remember exactly what it was, but it was something along the lines of there were people would get heart attacks. And so this is the data that was reported during a short period of time, where what we see here in this, what we call contingency table, and so we call this thing a contingency table. And a contingency table just shows certain outcomes and how frequently those outcomes occur. So the way we can interpret this is that there are certain times where Gilbert was on duty, which 40 plus 217, that's going to be 257 instances or 257 patients when Gilbert was on duty. And then, of course, there are probably more patients when she was off duty. So 34 plus 1350 is going to be 1384. And so of the percent of the times that Gilbert was on duty, we noticed that of the 257 patients she saw, 40 of them died. And so if we wanted to know what's the probability of, for example, just someone dying in general at this hospital during this time period, we would need some additional totals here. In fact, we would need to know how many patients there were in total. And we can just see that if we add up all the patients in these 4 squares, we get 1,641, which is the same thing as adding these pairs of numbers first and then adding those totals together, as well as down here. So 74 total patients died over the period of this time during which this data was recorded, and this will be 1,567 patients that did not die while during this period of time while at this hospital. So in either case, we add 74 plus 1567, we get the 1641. Now I could answer some pretty interesting questions about this. If I wanted to know, for example, what's the probability or what percentage of patients died, and now I'm going to give these names. If somebody died, we're going to consider all the people who died to be in the set D. And all the people who did not die we'll call D complement. So Gilbert was on duty. I'm going to think I'll just go ahead and use G for Gilbert was on duty and G complement for G, she was not on duty. Now, if I want to know the probability of that somebody had died while at this hospital during this period of time, then what I would want to say is, okay, how many people died? What's the size of set D divided by the size of the sample space, which in this case is 1641 because that's how many patients we have. And 40 of those patients died. And when we look at that probability, that number comes out to about 0.024 or 2.4%. So there's basically during this time period, there's a 2.4% chance that if we were to draw somebody at random, that they had died while in this hospital. And of course, we would expect the probability of somebody not dying to be 1 minus the probability that somebody did die. Now we should also point out at this juncture, we have our notation here, P of, so the probability of an event. And sometimes you'll see maybe lowercase p of D, sometimes you may see PROB of D. I prefer this one right here. And one thing we should note is that if E is an event, is some event, then the probability of an event has to be a number between 0 and 1. So 1 means it happens 100% of the time, 0 means it never happens, and then anything in between. Now we always talk about these as decimals usually, sometimes as fractions, but never do we actually get percentage values like 2.4 because the probability has to be a number between 0 and 1. And so if you think about the fact that if you look at all the people who did die and you add them to all the people who didn't die, you should get 100% of your entire population. So in this case, 1 minus 0.024, which is going to be 97.6% of people did not die. And that would be the same answer as if we took 1567 divided by 1641. Okay, but now we can look at some more interesting questions like, what's the probability that somebody died while Gilbert was on duty? And for now, without getting into the fancy notation that we'll get into later, while she was on duty. Well, while she was on duty, in this case, the sample space is the set of all people she saw while she was on duty, which is 257, and 40 of them died. So 40 divided by 257 comes out to about 15.5%. And if we look at the probability that a patient died while Gilbert was not on duty, right, we want to compare what's the likelihood of dying when she is on duty versus when she's not. Well, in this case, we have a different denominator because 1,384 patients were seen while she was off duty, and of those, 34 died. Well, already you can see that our numerator is smaller, but our denominator is much bigger, and so 34 divided by 1384 is going to come out to be a smaller number at around 2.4%. Now, it could have been that maybe she was the unlucky one that saw the patients during a specific period of time. But if you are an investigator or you are a statistician, this is very concerning. This is very concerning, right? Because we can see that nearly you're 7 times more likely to die while Gilbert is on duty than when she's not on duty. So either she's being a nurse or on duty during a time where there just tends to be more patients who don't survive, or there is really something that's going on here. That's just to illustrate that probability is very, very useful. This by itself would not hold up in court because there would need to be more details. We can't necessarily assume that there was foul play, but if you go look up Kristen Gilbert, I'll let you do that. She was actually convicted. It turned out that she was doing something she shouldn't have been doing. So this is just sort of an introduction to probability. You can see that sets are at play, and we'll start to investigate some more of the properties of how do we look at probabilities of intersections of sets, how do we look at probabilities of unions of sets in order to become better data analysts.